First of all, we're going to start with the absolute value function. We've already talked about this in the super secret notes. So in our absolute value function, that's where you have the y equals and then these two bars with an x in between. And if you were to draw a picture of that, it would look something like the following on your graph normally. And then we're going to talk about kind of what happens with that graph as we move it around and stretch it and shrink it. And so the first thing that you need to know about is a rigid transformation. And a rigid transformation is one in which you can move a function up, down, left, right, or you could flip it. Those are rigid transformations. The size and the shape stay the same. Bless you. So rigid transformation, the size stays the same, you just move that actual picture around. You'll see down below here they talk about stretching and shrinking of a function. Really what that means is like your absolute value graph will get narrower or wider if you're talking about absolute values, same with parabolas or anything else when you're multiplying or dividing by something. So if I had, as an example, y equals 1/3 times the absolute value of x, this would widen out my absolute value. If I had something like y equals 7 times the absolute value of x, this would narrow my absolute value, make it grow faster so it looks skinnier, closer to the y-axis if it was at the origin with its vertex. And this is really what they're talking about with stretching and shrinking. They're talking about these numbers that are in front of or even inside the absolute value. So I could actually take, if I wanted to, instead of writing y equals 1/3 on the outside times the absolute value of x, I could have written this as y equals the absolute value of x over 3. Because dividing by 3 and multiplying by 1/3 or multiplying by 1/3 is really the same operation. Likewise, just to show you, it doesn't really matter whether or not I have the absolute value inside or outside. Those two things are exactly the same as well. So whether we put the absolute value around the number that's multiplied by the x or divided by the x or not is not going to make a difference whether it stretches or shrinks, just so you know. Sometimes they'll put it inside, sometimes they'll put it outside. And all this is doing is making a graph look a little bit different. So for example, in the left-hand one, if I were drawing a regular absolute value like the following, then what would happen is if I did the 1/3, what you would see is a graph that looks something like this. It would get wider. Whereas if I did the absolute value that you see on the right-hand side, and I have a normal absolute value, what you would see when you redrew it is you would see one that had gotten skinnier because its rate is faster, 7 times as fast as the normal absolute value. And what they want you to understand is we've talked about rigid transformations, which means the same shape is there and it didn't change, wider or narrower. And today we're also going to talk about making it wider or narrower, or increasing at a slower rate, increasing at a greater rate. That's kind of the big idea. So down below here is a normal absolute value graph, I guess, if you will, that you see pictured in the red. So this is the absolute value of x. And they want to know what happens when you see 2 times the absolute value of x. And what I want to tell you is, if you ever get in doubt, we have skills from algebra that we can always use to kind of see what's going on. So if I looked over here and I made a table for this 2 times the absolute value of x, I can make an xy table, and I could plug in some numbers like -2, -1, 0, 1, and 2, and see what pops out for the y value. For example, if I plug in a -2 in for x, I have the absolute value of -2, which is 2, times 2, that's 4. If I plug in a -1, the absolute value of -1 is 1, times 2 is 2. If I put in a 0, I'll pop a 0. And it's a symmetric graph, which means it looks the same on one side as the other of the vertex. So this is a 2 and this is a 4 for the 1 and the 2. And when I plot those points, I have 0, 0, I have 1, 2, I have 2, 4, sorry, and it's mirrored, it's mirrored on the left-hand side, so I can do the same thing on the left-hand side. So 1, 2, and negative 2, 4. And what you can see is what we were talking about just a little bit ago, that because the 2's there, it's growing twice as fast. And what you see is a skinnier absolute value graph because it's going twice as fast when it grows. In letter B and letter C, just like in letter A, they draw the original graph. And then what's happening is they're saying, oh, look at these other ones. And if you remember just a little bit ago, we talked about that this graph is really the same thing as saying y equals 1/3 times the absolute value of x, because dividing by 3 and multiplying by 1/3 is the same. So if I were making a table for this one off to the side, I would pick some strategic numbers for x and y since I'm multiplying by 1/3, or in other words, I would pick numbers that are divisible by 3. So if 0 is in the middle, then I would go with -3 for my first one to the left of 0, and -6 for the second one, and likewise on the right-hand side of 0 for x, so that I can get numbers that are easy to work with. So when I plug in -6 for x into my x over 3, I have -6 divided by 3, which is -2. Take the absolute value and you get +2. If you plug in a -3 in for x, you have -3 divided by 3, which is -1. Take the absolute value, that's +1. If you plug in a 0, 0 divided by 3 is 0, and it's mirrored on the other side. So as I look at these numbers, what I do is I go, okay, I have -6 and I'm at 2, so here's one of the points. At -3, I'm at 1, and then at 0, I'm at 0, and then I mirror it on the other side, knowing that it's symmetric. And what you can see is this graph has widened out compared to our normal absolute value of x. So our normal absolute value of x, again, was y equals absolute value of x, and that's what you see in the red. In letter C, very similar. Again, they try to trick you with a number on the outside and a number on the inside. One's being multiplied, one's being divided. The way that you could write this to maybe make it a little more easy to see is just pull the 3 out. Notice that it's on the bottom of a fraction, so leave it on the bottom of a fraction, and just leave the x on the inside. And so this is like saying 2/3 times the absolute value of x. And I prefer to write things as a multiplication rather than a division, because it seems easier to work with for me. I would make the same table as I made in the orange. The numbers will be a little bit different. In fact, every number that you see in the orange table on the right-hand side would just be doubled. And so that's really the only difference between the two tables. So instead of a 2, we would have a 4. Instead of a 1, we'd have a 2. The 0 would stay 0, and then there's another 2 and a 4. And we get all these numbers again by plugging the x values in for x over here, and then producing what's left over. All of these can be produced on your calculator as well. I just prefer to do it by hand because the numbers aren't so bad. If I plot these points, at -6 I'm at 4, at -3 I'm at 2, at 0 I'm at 0, 3 I'm at 2, and 6 I'm at 4. And so again, this is a mirror, and you can see that this is wider, or in other words, increases at a slower rate than the original absolute value graph. Why? Because it's 2/3 of the absolute value. So every height will be 2/3 of the other height that you saw before. In the next one, they talk about what's going on. So this is more about thinking about the problem. And so in part A here, they talk about, look at the original y equals absolute value of x graph. And then they say, all right, when you see this 2 that's in front of the absolute value, what's happening to every y coordinate? When you look at the 2, excellent, it's being multiplied by 2. That's it. And then in the next one, when they talk about the absolute value, and they say what's happening when you see this 3 on the bottom, what's happening to every y coordinate? Divided by 3, or you could have said multiplied by 1/3. You could say either way. So you can say it's been divided by 3, or you could have said multiplied by 1/3. So the way we approach it in our table is we multiplied it by 1/3, but really you could say divided by 3. They are the same thing. Taking half of something or dividing by 2, same. Now this stuff that we've been talking about for about a week now, these transformations, are not specific to absolute value, like in our super secret notes. They're not specific to lines or to parabolas. They work for any function. Doesn't matter what it is. So in the next couple questions, that's what they're doing, is they're saying, hey, what do you think happens when you see this? So now the original function that they're talking about is an x squared, which we know is a parabola. And then what you see is that this parabola has this going on here with the 3 in front of it. So what happened to every y coordinate? Multiplied by 3. Doesn't matter if it's an x squared graph, absolute value, line, square root, whatever. Now in this last one, they try to trick us a little bit. Notice how in all the previous ones, you see that the 3 is with the x thing, right? And so what you see is what you get. In the last question, what you should notice is that the last thing here is with the y instead. And they want to know, if I multiply the y by 2 instead of the x thing, what actually happened to the y value? And when we put it with the x, that would have been a 2x. We would have said every y value was multiplied by 2. But now it's with the y. And remember, we always want to get the y alone. So instead of being multiplied by 2, every y value is divided by 2. And that's because it's with the y instead of x. So when you see it with the y, it's the opposite of what you would think. Kind of like when we're working with the things on the inside of parentheses.